Right, we've got a speed time graph going on here. State the acceleration of the car after 20 seconds. That's going to be somewhere here. And actually, it's going at a constant speed. It's not accelerating at all, and so it's simply 0. Find the total distance travelled by the car in the 30 seconds. Now, we learn early on that speed is distance divided by time, but that's actually only true for the average speed. Now, what do we do if we want to find, so distance would be speed times time if you have the average speed. What do we do, however, if the speed is changing? Well, there's something a bit more complicated, and that is, it works for this one. It's you would just do the speed times time, so you would do 18 times 22. What do you do when it's increasing? Well, it's the area. It's actually the area under the curve, and so here I can simply do the area of the triangle, a half times the speed at the end times by my 8, and there I have it. Really, I just need to work those out. So it's going to be 0.5 times 18 times 8, which is 72, plus 18 times 22, which is 396. And that's going to give me my answer of 468 meters. So that's how we can deal with that. The speed v of a train is 68 kilometers an hour. Correct the nearest kilometers an hour. Write down an inequality to show the error interval for v. Okay, so this is a lower and upper bound question. So the smallest it could be would be 67.5. And that would round up to 68, so it can equal that as well. And the upper bound is 68.5, but it cannot equal that, so we don't put the equals bit in. That is our error interval. Let's keep going. Graph shows the distance travelled by a lorry in 12 seconds. So now we've got a distance time graph. Estimate the speed of the lorry after 5 seconds. So here we are. What is the speed going to be? Well, to do this, we're going to need to find, to draw a tangent and be able to work out the speed at that instant. So let's get our ruler out. Just realized I need to get my, okay. I think my ruler's up here, right, bear with me. So you need to move it so that it just touches. I think I'm going to do a bit better than that. I think I can move it even more. So it's just got to glance off the curve. I'm happy with that. And now, essentially, draw a line as all the way along the graph. Okay, the longer you make it, the less error you're going to get when you're reading off of it. And let's use the full width now. Yeah, because basically what we're doing, what we are doing here is we're doing the fact that speed is equal to distance over time, but it's my change in distance divided by my change in time. So I'm working out my gradient, essentially. That's what your gradient is. You change your rise over your run. We're doing the same thing here. So the change in distance is going from 0 to 46. So this is actually, I shouldn't write equals. It's going to be approximately 46. And then my time is 2 to 12. So it's going to be 10. And that's going to give me 4.6 meters per second. So that's only in this single instant, but I use the gradient, the instantaneous gradient, essentially. I draw this tangent And that allows me to do it. This is a very powerful method. I've not really gone into why it works. I've talked a little bit about it, but that is how you deal with this sort of question.